All right, so yeah, I'm gonna talk about today like tree topologies along a tropical line segment. This work is a joint work with Shelby Cox, and she is a student of Dr. Spears. So all right, so let's start it. All right. So I am interested in phylogenetic trees, and this is a picture. Actually, this data set, that's like really motivation for me to work on this tropical geometry and also application to phylogenomics. So when you take first time biology class in high school or wherever, but in biology 101, basically you learn that our ancestors came from ocean, right? So this problem, biologists really want to understand how our ancestors migrated from ocean to land. Okay, so the tetrapod, you see this. They are basically land living things, like something like lizard, mammals like, mouse or whatever. And this lungfish, this is a fish with lung, and also this is a coelacanth that basically, looks like really like ancient fish. And biologists want to know that lungfish or coelacanth, which one is closely relating to tetrapod, land living things. So phylogenetic tree is a tree representation of evolutions between species. And, you see, if you see before Darwin's notes, Darwin draws some actual tree looks like, and that's representing the finch's evolutions, and that's the phylogenetic tree. So this is a phylogenetic tree, and leaves of the tree, those are living things or living species at a current time. And those branches, basically, internal branch, that's the common ancestor of those like, ancestral nodes. Okay. So here you notice that like lungfish and coelacanth and also common ancestors of the tetrapod. So you see this, that's intentionally like this picture, it's not clear which one is closely relating to the common ancestors of the tetrapod, because just we don't know. Okay. So this data set, actually coelacanth data set was actually whole genome data set, was sequenced in 2013, and that's actually published in Nature. And soon after that, biologists actually aligned all genes from the whole genome sequences for the lungfish, coelacanth, and tetrapod. So that's actually I used, and I wanted to understand that, which one is closely relating to, and why it is hard to distinguish the lungfish or coelacanth, which one is closer to tetrapod. I just wanted to understand. Okay. So classic phylogenetic tree reconstruction. That's basically we have a sequence of DNA sequences or RNA sequences or protein sequences. I don't care, that's a DNA or RNA or protein sequences. So that's the basically input. And for that, just constructing one phylogenetic tree, output is a tree. Okay. So in this talk, I assume that actually this problem, it's been done like a lot. I don't say done. Actually, there are tons of people still working on this. But this phylogenetic tree reconstruction, this problem has been really worked since like a long time ago, like especially application to genetic data that's actually been working on since 1960. So there are so many great methods for phylogenetic tree reconstruction. So for me, this problem, I am not actually like focusing on just reconstructing one tree. I focus on actually analyzing on a set of phylogenetic trees coming from the same genome data set. So in genome, you can actually find there are tons of like genes, and for each gene, we have sequence, like DNA sequence or RNA sequence, and I assume in this talk it's aligned, and for this step from each sequence, we have tree reconstruction, and this step, I assume that we have good estimate of gene trees. That's the phylogenetic trees reconstructed from each gene. Okay, so from there, we have like a sample of phylogenetic trees, bunch of trees, and in order to do, some statistical analysis on a set of trees, we have to do something. So we can actually vectorize somehow each phylogenetic tree. And I will explain that. Actually, I'm going to go back a little bit. I forgot one thing, that for the phylogenetic tree, each leaf has a label. The label is basically that's a name of species. But for internal node, it doesn't have label. And also, it has the branch length. The branch lengths basically represent mutation rates and also evolutionary time. Okay. All right. So go back to the coelacanth lungfish data, and for the data set, they clean up basically align the sequences, and also, of course, they did the gene finding. So data set consists of 1290 genes, and from there, you can construct about 1,300 gene trees. So we have 1290 gene trees, and with 10 species. And so the original paper, they looked at all gene trees, and they looked at the tree topologies of each gene trees. And basically, we have 4 kind of gene trees like this, like tree 1, tree 2, tree 3, tree 4, and about just uniformly distributed that gene tree topologies. So, 25% of that's tree topologies have tree 1, 25% of gene trees have tree topology, looks like tree 2, and so on. So from that, just simple analysis, it was not clear. Lungfish or coelacanth, which one is closer to tetrapod? And here, that's this guy. That's basically it's called auto group, and that's the sharks group basically. Okay, so yeah. So they wanted to know that, how, I want to know that, more closely how that, tree topologies or gene trees are distributed over the space of all possible phylogenetic trees. That's what I wanted to understand. So simple-minded, long time ago, that okay, I vectorize each gene trees. Somehow I'll explain to you guys later. But then just I applied. So it's all vectors, and that's in a Euclidean space. I thought, oh, I gotta just apply PCA. That's a simple one. I just do this. And I actually plot those, plot this guy. This is actually three-dimensional pictures using, that's kind of hard to see the one dimension, but that's a three-dimensional pictures. And I apply the PCA so I can visualize. And from there, I saw clearly, just clearly two separated clusters. So I thought maybe this is why, lungfish or coelacanth, it was not clearly, separated because we have two clusters. And actually, I was playing with this picture actually this is actually plotted from MATLAB. And in the MATLAB, you can actually see this from the different angle and so on. So I was kind of looking around and I thought, wait a moment. It looks like a shape of the tree space. It's called, I will explain a little bit. That's a space of all phylogenetic trees. And I thought, looks like that tree space. So, maybe classical PCA say that it's a two cluster, but just basically that they didn't capture the space of phylogenetic trees, so that was confused. So that was a really motivation that I wanted to develop a PCA over the tree space because I really wanted to do right thing. So after this, we actually, my colleagues and I developed a couple methods for PCA, mimicking that PCA technique over the space of phylogenetic trees. So the difficulty of the space of phylogenetic tree is that it's inside of the Euclidean space. However, the problem is that that's the union of the polyhedral cones. So you can imagine this is kind of, combinatorial representation, but basically, so it's for rooted tree with 4 leaves. That polyhedral cone has that's a 2-dimensional polyhedral cone, but basically it's glued together. It looks like origami, and we have that origin, and it's just going shooting to my screen. That looks like it basically. So it's not convex. Classical meaning of the convex in a Euclidean space. So if you just directly apply the classical PCA, we get something that it's not really as you saw this here earlier, you might see this some two clearly separated cluster, even though they are actually not. So this is the problem, and we have this, and also the space of phylogenetic trees. This is not, like I said, classically convex, and also the polyhedral, we have the polyhedral cone, that's so much lower dimension than the Euclidean space, which it's embedded. So so basically that if you just apply classical PCA to the tree space or the data sets on the tree space, it's not really easy, or I don't think this is the right way to do the analysis. So that was the trouble we had. Okay, so one of the PCA-like method I use, that's called tropical PCA. So basically, I apply the tropical geometry to the basically space of phylogenetic trees. The reason why I could do that is that the Bernd and Spear and also a bunch of people, they showed that the tree space. So you see this looks like this right now, but you can just see this root, origins here and just shooting up. The space is actually tropicalization of some linear equation, linear space. So basically, this space is a tropically convex. So if I take that like vertices, so here this is a tropical triangle, and we have 3 vertices, and I forget which one is the vertices, but those 3 vertices are actually, that's the vectors representing trees. So those vertices are in a space of phylogenetic trees, and we actually take the tropical convex of those vertices. This means that this triangle, that triangle is inside of, guaranteed to be inside of the tree space. So basically, this is the tropical polytope or tropical triangle. Inside of the, basically, that's inside of the tree space. So all points inside of this tropical polytope best fit tropical polytope to the data set. That's what we did. And then, so we try to find, so we have the data set in all over the tree space, and then we try to calculate that, tropical polytope, so that the sum of the tropical distance between the projection onto this polytope and each data point is minimized. So that's we say that principal tropical polytope, and that's the best fit tropical polytope to explain this given data set. And those actually all color points, those are projected points from observations, given observations, and you see this that all like black dots are basically that tail of the distribution, because there are so many topologies. But we change the color. So we change the colors, and depends on what kind of tree topology looks like, and just we color them. So you notice that, like in each cell, so you see this each cells of the triangle, it seems like same color. And actually, we proved that one of the paper, actually this paper, this paper, we proved that yes, indeed, if you pick the 2 points inside of the same cell, then they have to have the same tree topology. We proved that. But the difficulty for biologists or for us to interpret this triangle, because, like, for example, this cell, I have no idea what kind of topology looks like. Or this cells, I don't know what kind of tree topology looks like. And in general, that, like, if I go along those lines, and how tree topology gonna change? Because all we showed was if I pick the 2 points from the same cell, then they have the same tree topology. But I don't know how tree topology changes over the next to each other or along this line. I have no idea. So that's really, I think that's really important. Because for statisticians, like for me, the interpretivity of the output is very important. So, you can see this, the visualizations of data set, like PCA. You can see this. This is a two-dimensional representations of how gene trees are distributed over the tree topology. But if I don't know, like those tree topology, how they are changing it, it's kind of hard to interpret. So this is the really motivation why I wanted to understand that how tree topology changes over the tropical geodesic. And I'll explain in a second. Do you have any questions so far? Okay. So in this talk, another assumption. I assume that all tree has equidistant. So they are equidistant trees. So this means that from root to leaf, it has the same distance. So for example, from root to leaf A, we have 2. And from root to leaf B, that's 1 plus 1, that's a 2. And from root to leaf C, that's 1 plus 0.2 plus 0.8, that's a 2, and so on. And this assumption, I don't think this is a really bad assumption because remember, we are interested in phylogenetic, all trees are phylogenetic trees, and you see this in the beginning, that current species are present, and I assume that they have the common ancestors, and the distance or, evolutionary time or evolutionary clock, they have to have the same time anyway. So, if I assume the evolutionary clock or time, then I think that's not a bad assumption. Okay, and this is how we vectorize. So, we take pairwise distance first. And so, for example, we have 5 leaves here. So we first create a 5 by 5 matrix, and we calculate all pairwise distances. And for example, here, this one AB coordinate, and that's 4 because I calculate distance from A to B, that's a 2 plus 1 plus 1, that's equal to 4. And if, for example, I take this CD element, so calculating the distance from C to D, that's 0.8 plus 0.5 plus 0.3, that's 1.6. Okay, and so on. And you notice that diagonals have to be 0, and that's a symmetry. So I take just upper triangle part of this matrix. And then we lexicographically just order them. Okay, so this is how we vectorize a tree. And if actually, this is a quick fact, if we calculate this similarity map from phylogenetic tree, and especially equidistant tree, that's actually unique, and that's a 1-to-1. So if I have that like this vector, then there exists a unique tree representing this vector. Okay? So I can recover, go back and forth. All right, so this is actually key fact. And this is also, this matrix, this has a special format. So, special property. So, for example, this is called ultrametric. And ultrametric means that if I take that for distinct leaf, IJK, max of distance from IJ, and distance from JK, and distance from IK, the max among all three, they achieve at least twice. Okay? If this satisfies, we call ultrametric. And I know that if actually this tree is equidistant, then this similarity map has to be ultrametric. That's a if only if relations. Okay, so instead of looking at the space of all equidistant tree, now I look at like space of all ultrametrics because that's one-to-one correspondence. So this is equivalent. So now we look at the space of ultrametrics, and that's the other tree space. And as I explained before, this space is a union of lower dimensional polyhedral cones. So, when we are trying to develop the PCA or any kind of machine learning method over the tree space, it's not so easy because it is a union of the lower dimensional polyhedral cones. And also here is that as I said, the space of ultrametrics, I denote the UN. This is a tropical linear space, and that's basically the solution set of the topologization of a linear equation. Okay, so yeah, that's a quick fact. All right. So before going into this, so this is why I would like to use the tropical geometry because this is a fact, and also the tree space is a tropically convex, and also the tropical polytope is also tropically convex. So that means that if vertices are coming from space of ultrametrics, then all points along the polytope or like line or whatever, they have to be inside of the space of all ultrametrics. And we don't have to think about that. So it's like almost like kind of applying like linear algebra in a Euclidean space. It's not that simple, but it seems like doable. This is why. This is the reason why I'm using a tropical geometry for developing machine learning method and so on. Okay. Any questions so far? This is just a motivation, and of course, talking about the motivation took me 30 minutes. But all right. Really quick, I'm going to talk about the basics from tropical algebra. Okay, so we are using max plus algebra. So what it is? What is it? That is that I define the addition, that's a max of A and B, and here A and B are real numbers, and also the A times B, that's I just use addition. And also the tropical distance. So in order to do any, statistical learning over the space, we have to define the distance measure and distance metric. And here we use this is called tropical metric or tropical distance. So suppose we have two ultrametrics. So that's a V and W, and tropical distance is defined as max of the difference minus mean of the difference. Okay, so this is known as the generalized Hilbert projective metric. And this metric is well-defined metric over the, this is called tropical projective torus. The reason is that we have to model by 1, 1, 1, 1, 1, 1, 1. So, or like constant. So the reason is that if actually I don't mod this guy, then it's no longer metric because, so remember, in order to be metric, you have to have that, this metric equal 0 if only if B equal W. But if I don't take the mode, that's no longer like this. Like, for example, B equal to 0 and W equal to, like, let's say, like some, like 1, 1, 1, 1, 1. Then, you know, I take the difference, that's going to be max of the difference equal to mean of the difference. So that's going to be equal to 0. So in order to make it this as a metric, basically we take the old mode. This is why we actually focus on tropical projective torus. But just that's a small detail. Okay, so tropical polytope is a basically, suppose we have a finite set from the like tropical projective torus, and then just basically we take the like tropical convex, that's the like basically like x and y, those are vectors, and a and b's are real numbers. And the tropical convex hull is defined as this guy. So V is a finite set from the vector space, and A1 through AR, those are real numbers. So it's slightly different from the classical polytope definitions or convex hull definitions, but for under the tropical geometry or tropical arithmetics, that makes sense. So if I take that like just 2 points, like suppose we have V that consists of just 2 points, that becomes just a line segment. And this is a special case, and we look at this tropical line segment very closely, because actually, in fact, that this tropical line segment is a geodesic. That means the geodesic means that like we take 2 points, and that's the shortest path in like between those 2 points inside of the space. And in fact, that this tropical line segment is a geodesic over the tropical projective space. And if I take the 2 points, those are ultramatrix. Then the tropical line segment, this is a geodesic inside of the space of ultramatrix, and also the like all points along the geodesic, they have to be inside of the space of ultramatrix. So this is actually I really want to understand what's going on, but tropical geometry. So tropical geometry, just they care only like, you know, like ultramatrix. That's like special, like, you know, structured vectors, right? And there is nothing to do with, okay, that's not nothing to do with. There is a relation, but it's implicit. It's not explicit. They don't, I cannot, at least I don't see that like tree topologies of the equidistant tree. And ultramatrix, like I said, if I pick a ultramatrix from a space of ultramatrix, there is a tree, equidistant tree, right there. You can calculate, you can reverse it, you can calculate. However, like, you know, it's not clear. It's just still not clear. You have to calculate it. But it's not obvious. Like, especially it's not obvious that you calculate the tropical line segment. I know that that's a geodesic, and all tree, like all points in a tropical line segment are ultramatrix, but I have no idea. They are corresponding to equidistant trees. However, I don't know the tree topology. I really want to understand the combinatorics of the tree topologies along this tropical line segment. This is my motivation, and this is the question I would like to answer. Okay. So this is a theorem. Basically, basically that we show, this is another paper, tropical line segment between 2 points is an intrinsic. That means that it never leaves outside of the space of ultramatrix, and that's a geodesic. And also, important thing is a unique, because tropical geodesic, they don't have to be unique in generally. But for the tropical line segment, it is unique. This is also another thing that's important. All right. So first theorem. Okay. So suppose that we take like x and y randomly. Those are ultramatrix, and so like let's say like randomly means uniformly. Then the probability of that like this tropical line segment containing the origin, that actually probability is equal to 0 if n is greater than or equal to 5. So this is actually important because there is another matrix that's also intrinsic matrix that's called Borel-Holmes-Bogman matrix. And that matrix is a great because it's naturally, it is coming from the really tree topologies, tree structures. So the like the geodesic, the BHB geodesic, you know exactly how tree topology changes because it's really coming from the tree topologies. But the geodesic, like the probability that random two trees, we pick random two trees, and the BHB geodesic containing the origin, that's not equal to 0. Actually, that's a positive probability. So this is not good because that means that it's like always, origin is actually dragging the geodesic all the time. So it's kind of not really, it's put so much weight, and that's actually stickiness. That's we call the stickiness, and causes a lot of problem for like machine learning, statistical learning using the particular metric. But the tropical metric seems like it doesn't have it. So that's actually really important theorem. And for the n equal 4, actually n equal 3, that's too small space. And here n is a number of leaves. Sorry, I forgot to say that n is a number of leaves. And n equals 3, basically BHB matrix and tropical matrix are basically like isometric. This is why it's not true. And n equals 4, still it's too small for this statement to be true. But if number of leaves is greater than equal to 5, yeah, the probability is actually equal to 0. And the proof is basically, I use the lemma 3.3, that's from my old paper, that in order to tropical polytope to contain the origin, you have to satisfy some conditions. So this is lemma I use to prove that this theorem. That's just like couple minutes version of the proof. All right, I'm gonna finish quickly. So another thing is that another theorem is focus on the clade. And before stating my theorem, I'm gonna say that like define a clade. And I tried to write down the formal definition of the clade, but it was too long. So I just gonna show you picture. Basically, clade is that if I chop off some actually one branch, on the top, then that still form a equidistant tree. So for example, I chop off this actually edge, internal edge, and that form a equidistant tree. So this is a clade. And also this part blue, I chop off this edge, internal edge, and it still forms a equidistant tree. And so this is a clade. But the green part, it's not true because I chop off this edge. But also, in order to just focus on pure green part, I have to chop off this guy too. So it's not a clade. So green part is not a clade, but the subtree, inside of the orange and inside of the blue, they are clade. All right, so this is a quick definition, informal definition of clade. All right. So the second theorem is that, so suppose I have the two trees, equidistant trees, and I draw a okay, so two trees, and they share that. So we have the, like, so for example, two trees have some clade, like let's say this red part, and the clade which they share, they have the same tree topologies. Then the tropical line segment between those two trees and the part of the like subtree, they have the all tree topologies along the tropical line segment. They have the same tree topology in a just subset of the like clade. So the basically all tree topologies along the tropical line segment, this part of the tree have the same tree topology. Okay, so that's the second theorem. Okay. Then the third thing is that, like, we're gonna define nearest neighbor interchange move. So X3, X1, X2, those are clade. That's the, like I defined before. And nearest neighbor interchange is a tree move or tree change, like basically changing the tree topology by the, so you fix still all clade tree topologies, X1, X2, X3, but basically the edges. So here it's the X3 part is loner, but here now X1 part is loner. And or we can put X2 part of the clade, that's gonna be a loner. So this actually changes the tree topology. So from this tree topology to this guy or this guy, like going to left or going to right. So this is one nearest neighbor interchange move. That's what we say this. Okay. So another theorem we showed was basically if we have two tree topologies or two trees, two equidistant trees, and suppose they only differ by one nearest neighbor interchange move. So tree 1, T1 might be this guy, and T2 might be this guy. Okay? Then the all tree topologies along between, like along the tree tropical line segment between those trees, they have the tree topology equal to T1 or T2, or some branch length might be 0. Okay? So it's basically like, what's happening is that, like, okay, so suppose this is a T1 and I want to move T2. And then basically the all this edge becomes 0, and it looks like basically just hanging, like T1, T2, T3, that's all hanging like this, and then just branch out like this. And that's happening, like tree topology looks like along a tropical line segment between those trees. That I can show. But So this is a conjecture. That's a big conjecture. I want to generalize it. I thought I had it. I really thought I had it, but I realized that some actually mistake and my proof was not complete. So this is like my conjecture. So I want to generalize it. I would like to see that for any trees, namely that, so suppose I have T1, I have T2, and then all tree topologies along a tropical line segment changes by nearest neighbor interchange moves. So that's a sequence of the NNI moves. And I really thought I had it, and just it was just like, yeah, I really tried to use the relation between the like BHB, that's a Borella-Holmes-Bogman metric, and I tried to use the relation between this BHB metric and tropical metric, and I really tried to do that, but I did just small details. I couldn't really get it, and that's kind of why I just couldn't prove that this conjecture. But if you can actually, if you have some idea, or your students or someone who are interested in, please let me know. And really, I think that this is the most basic question for developing statistical learning models over the space of phylogenetic trees. And I think just, until we don't understand how tree topology changes, I think it's harder to interpret the output. And yeah, so this is a still hiccup that I cannot really advertise to biologists. And yeah, the reason why BHB metric is so popular among biologists is that I think the interpretivity. And I really think that's the key problem. So yeah, if you are interested in, please let me know. And thank you so much for your attention. And my paper is on the archive, and it's going to be appear in a special issue of the Vietnam Journal of Mathematics. Thank you so much.